Welcome to 23rd class meeting of EECE574, the graduate level probability and random processes. As usual, homework 12 will be assigned, and you can download all the handouts for chapter 6 of Peebles textbook. We are here at the something's not correct. I believe it's 6. Seven. Yeah. So we are studying temporal characteristics of random processes. So mostly we are talking about the samples of a random process, whether it is a discrete time or a continuous time. So last time we defined what is a random process. And as always, we started from the underlying probability space. So we have a box here that shows how the probability space is constructed. And here comes the outcome. And here we have an interesting mapping rule, which is parameterized by T and S. So unlike the previous mappings, we may have this T set an element of a continuous set or a discrete set, anything. For a discrete time, for a random sequence or sequence of random variables, we had some natural numbers, right? So we are kind of expanding our definition. This T can be a member of a finite interval, which is a continuum, or it even can be the set of real member of the set of real numbers. In this case, our interpretation is not that we can observe only one sample path. It's like we observe, still we may observe many samples. Otherwise, this application of probability theory does not make sense. If you can observe only one sample, why you apply probability theory? The reason why we apply probability theory is that we may observe a lot of outcomes. You may say that still I can compute the probability. But as I told you, probability is a special kind of expectation. So what is this? This is the probability of event that your random variable, for example, is a member of the event A, right? And also, due to the law of large numbers, what is this? This is well approximated as arithmetic average of n indicator functions. What does that mean? Expectation requires us to observe many outcomes. And expectation is actually a special, generates a special, the probability is actually a special case of expectation. What does that mean? Probability, for it to make any sense, we may have to have many observations, possibly independent observations. So never forget this. Right? There are two ways to handle uncertainty in electrical engineering. Actually, we do not teach the other part, but it was once famous and very useful. That is the chaotic theory. So in order to handle uncertainty, you may model something probabilistically, or you may model it as a chaotic theory, a chaotic system. Sometimes that chaotic system is approximated by a nonlinear recursive model, something like that. Anyway, so here, as usual, we denote the output without this parenthesis and s, as we've done it for random variable, random vector, random matrix, and even a sequence of random variables. So everything's the same. However, if you take a look at this one again, we can view this random process in two different ways. The first one is this. Suppose we fix S. So we have some specific outcome from our random experiment. Then what is this x sub t of S0? That is a signal, a deterministic signal. From what? From the ensemble. Okay. So the ensemble is the set of all possible sample paths. So this is a deterministic function. Function of t. Another one is we fix t to t0. Then what do we have? Now this is a single measurable function of S. What is the name of that? A random variable. So this is a random variable. What does this mean? What does this second point of view mean? Given a random process, how many random variables do we have? Uncountably infinite or countably infinite, depending on what is this set that parameter that this t is a member. For example, if t is an integer, how many random variables do we have? Even though we have a single box, actually, you must view it as a countably infinite number of random variables. That is a measurable function. Each of which is a random variable. Got it? What about this one? Still, you have uncountably infinite boxes because you have uncountably infinite real numbers here. Same thing here. Got it? So a random process means that you have uncountably infinite number of jointly distributed random variables. And you know how complicated it is to describe, fully characterize a random vector. For example, the random vector has 100 elements. Then your full characterization requires usually 100-dimensional CDF, right? Now you have infinite number of random variables. So in general, it is impossible to fully characterize a random process because it's too complicated. However, there are some very special cases. Or even though the full characterization is very complicated, we only need a partial characterization for our application. So whenever we have too complex something, don't be frustrated. You just need to state that it's too complicated because of blah, blah, blah. Then you may say that, let me partially characterize this one, and I provide you some useful things, something like that. Got it? Anyway, so this graduate version is very important, but still, this major theoretic point of view is very important whenever you want to generalize something with uncertainty using probability theory. Random graph, random field, random polynomial, random anything. They have the same form. Got it? We start from the underlying probability space, and then we have some mapping rule to have the entity we want. Got it? So field, polynomial, graph, anything is possible. And I just mentioned two types of infinity, countable infinity and uncountable infinity. And also, I briefly reviewed engineering or practical meaning of plus minus infinity for the time parameter. For sufficiently past or sufficiently far future, something like that. You should not interpret it as from the Big Bang to the big crush of our universe. Never do that. Okay. Okay. So so we have just kind of classified random processes as a continuous parameter random process and discrete parameter random process. However, each random variable may be a continuous random variable or discrete random variable. So we have 2 times 2, 4 classes of random processes: continuous time, continuous random process; continuous time, discrete random process; discrete time, discrete random process; and discrete time, continuous random process. And we've also seen some examples. Of course, we have some other classifications like deterministic random process and non-deterministic random process. Here, you must be careful with a deterministic function modeled as probabilistically. For example, your system source always generates signal x of t. In that case, you may say that with probability 1, your random process equals x of t. Got it? This is not the definition of a deterministic random process. This is just deterministic signal modeled probabilistically just for convenience. Deterministic random process means that if you observe up to some time instant about this realization, and then you can perfectly predict the future. Of course, you may say that that is useless, but in some applications, that is very useful. So remember that. However, most of the random processes are not deterministic. They are non-deterministic random processes. What does that mean? Even though you have the full observation of a sample path up to some time instant, you cannot perfectly predict the future evolution of the random process. In that case, the random process is called non-deterministic. Got it? And then we moved to the second section, where we started by asking ourselves to how to fully characterize a random process. And there are 2 ways. The simplest one is to rely on our definition, measure theoretic definition. So for each sample path, right? For each sample path, what is the probability for it to be the output? And there was the simplest example like this. So here, we had S is either heads or tails with the probability P and 1 minus P, or at that time I remember 1/3 and 2/3, something like that. And for heads, this mapping rule gives you cosine 2 pi ft, cosine 2 pi t, I remember. And for tails, sine 2 pi t. Got it? In that case, we just need to know what is the probability of this sample path to be selected or that sample path to be selected. And this fully characterizes this random process. But not every random process has this simple rule. There are many complicated ones. For example, as we've seen last time, that is actually Bernoulli random process with the probability P. We have a discrete random process that takes either value 1 or 0. And also xn's are IID. So you have a sequence of numbers, either 0 or 1. And then let me ask you a question. What is the probability of this specific sample path to be realized, what is the probability of event that you observe this sample path? All 0. And you already know it's 0. What if all 1, 0? Actually, any sample path has probability to be realized 0. Why? Because you have uncountably infinite sample paths in this case. So even though individual sample path has probability 0, if you define something like, okay, you group the sample paths having the zeroth entry equal 1, then what is the probability of you're observing one of those sample paths? Then you easily know that is P. Got it? So even though individual sample path has probability 0, if you define an event cleverly, then it has non-zero probability. Got it? So it's similar to a continuous random variable. You have, for example, standard Gaussian. What is the probability of event that your realization of random variable x equals 0? Probability is 0. For any value, a real number, your probability of observing that number is 0. However, what is the probability that you observe something, some number greater than 0? That's 1/2. Got it? So don't be confused. Got it? Anyway, so in general, it's not easy to fully characterize a random process, but sometimes we may use measure theoretic definition, or we may use some non-measure theoretic approach. And the theorem that links these two approaches is the Kolmogorov's extension theorem, or existence theorem, or consistency theorem. And this Kolmogorov's idea is based on how we fully characterized a random vector. So suppose we have 100 length a random vector. Then, of course, we know that 100-dimensional joint CDF fully characterizes it. But what about 99-dimensional CDF, 98-dimensional CDF, 1-dimensional CDF? They must be all consistent in the sense that if you marginalize the 100-dimensional CDF to some nth-dimensional CDF, you must have the same thing. Got it? That is consistency. And Kolmogorov showed that even though you are given uncountably or countably infinite number of random variables, joint random variables that form a random process, for every finite number of random variables among those uncountably or countably infinite random variables, if you can find the joint CDF of finite jointly distributed random variables, and if they are all consistent, then it's equivalent that you have a measure theoretic definition. So there exists some function capital X sub T of S, even though we do not know how to write down the rule. Got it? So in that sense, we may either use measure theoretic definition, or just we may use joint CDFs. Got it? And when do you use the measure theoretic approach, or when do you use the joint CDF approach? That depends on your problem or situation. Got it? Anyway, so naturally, Kolmogorov's theorem requires us to define the first order CDF of random process, second order, third order, any nth order, any finite nth order joint CDF we need to define. the last topic of previous class meeting was the mean path. So given a random process x of t, what is the expected value of this one? First, this one must be a function of time. Why? Because for each value of t, you have a scalar. What it is? A function of t. So this is a function of t. Then how can you obtain it? It's formidable at the first glance, but if we fix t as t0, then it's just the expected value of a random variable. So we may use, for example, the PDF of a random variable like this. So here, for x of t0, we have the value times the PDF integrated. Got it? Now we drop subscript 0 here, then we have a function of t, right? So this is simply integration of x, density of x of t of x dt, and which is a function of t. So we have a function of t that is called now the mean path or mean function or the ensemble average of the random process. And interestingly, the mean path is not necessarily a sample path, as I told you. And let's take a look at this example. So what is the sample path given the Bernoulli random process, which is a discrete time, discrete random process, now with parameter p. And you have p for all n. Now, what if p is greater than 0 or less than 1? So it's, for example, 0.5. And this mean path has value 0.5 for all n, and there is no such sample path in the ensemble. Got it? So the ensemble average, the sample path or the mean path, may be drastically different from sample path. And we already actually know from our experience in random variable. Even though random variable is regarded as one of the most important representative number of a random variable, it's very, very misleading because there are uncountably infinite number of distributions having the same mean value, right? So as we know that even for Gaussian, we at least have two parameters, not only the mean, but also the variance. But what about the arbitrary distribution? We may require countably infinite moments of the random variable if it exists, right? Some random variables even does not have some n-order moments. Got it? So that just translates to the random process case. Mean path never represents the ensemble. However, there are some special cases where the mean path really means something. And those cases are also very important. However, never forget the fact that mean path may be drastically different from sample paths. Okay, here goes the preview. But we've already covered this Bernoulli random process with parameter p, which is a very special discrete time, discrete random process. And we are going to see a discrete time, continuous random process. And also we talk about stationarity to order 1, 2, order n, and strict sense stationarity, and Y-sense stationarity, and covariance stationarity, blah, blah, blah. And you remember your professor in undergraduate course talked a lot about stationarity. Is that important? And what is it? Actually, stationarity means that something does not change even though time passes, roughly speaking. Actually, that is not true. Stationarity means that your characteristic of a random process depends on the difference from some offset, time offset, something like that. But it can be just said that something does not change even though time varies. And as you may easily guess, this stationarity is a very, 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 very restrictive condition. So suppose this is the set of all random processes, the set of all imaginable random processes. What would be the size of this subset of stationary random processes? Probably smaller than this dot. Got it? However, in this state, we can not study. So here goes some stationary random processes. In some sense, there are many different levels of stationarity, as you've seen. Y-sense stationarity, covariance stationarity, even cyclostationarity, or stationary to order 1, 2, and strict sense stationarity. But anyway, all the subsets are very, very small compared to the entire universal set of random processes. But without assuming stationarity, it is very hard to characterize a random process. And vice versa, stationary random processes has very good, very simple way to describe it. Okay? Fully characterize the random process. So you have kind of trade-off. So given a true real-world random process you want to model, it may not be stationary at all. But if you model it as some level of stationarity, then you can easily handle that. So under certain condition, for example, you assume that is a stationary random process and analyze that. And if your analysis really fits well to the reality, then you may say that this model works good. However, always never be sure that your random process is really stationary. There are very rare cases in which your random process can be modeled as a random, the stationary random process. Anyway, so we will study a lot, and also I hope we can study Gaussian random processes. There are two types of Gaussian random processes. One is stationary, and the other is not stationary. So in stationary case, this is very famous, and as a communications engineering graduate student, you've already got confronted it already. And also, this case we are going to study immediately after this preview is a special case of Gaussian random process. However, there is a big subset of non-stationary random processes, and among which we also have a big subset of so-called Wiener processes. And that is also very important. And I don't believe I can start Poisson random processes today. Anyway, so let's start. So first example is a discrete time, discrete random process. So I denote it by capital X of square bracket n, okay? And each of this, which is a random variable for different n, is now modeled as a Bernoulli random variable with parameter p. What does that mean? Bernoulli means that you have actually two. However, Bernoulli more means that either your outcome is 0 or 1, and especially when you say that Bernoulli with parameter p, the probability of your outcome is 1 has probability p. Got it? So the probability event that you observe 0 has probability 1 minus p. Got it? And what else? You have in this case countably infinite random variables. And if you say that this is a Bernoulli random process with parameter p, you are assuming that these countably infinite random variables are IID, independent and identically distributed. Now, let me ask you a question. Is this statement, the previous statement, xn is a Bernoulli random variable with p and xn's are IID? These two lines, my question is that these two lines fully characterize this random process? In order to answer that, right, you may either show that mapping rule for the major theoretic definition, or you have to be able to find every nth order PDF or CDF or PMF. Which one do you want to take? Interestingly, in this problem, it's easier to talk about the joint PMF. So let's start with the first order probability mass function. What is that? First order probability of xn of x equals right? So this is the probability mass function, lowercase p subscript p of x over n. Okay, and as you see that this x can be any real number, but it has non-zero value for x equals 1 or 0. So this equation fully describes this first order PMF as a function of x. What about second order? You have to choose n1 and n2. So joint probability mass function of xn1 comma xn2 of x1 comma x2. What is that? Thanks to the IID assumption, this simply factors into the first order PMFs, right? So done, right? What about the third order? Same, fourth order, any nth order. Here capital N is not a random variable. So P, X, N1, X, N2, dot, 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 X, N, N. It's not a good notation, but, and what is that? Due to the IID-ness, we have the product of the marginal mass functions. Done. So we have just have found any nth order PMF. Now, are they consistent, right? They should be consistent in the sense that any marginalization of a higher order joint PMF must be consistent with any lower order PMF. Are they? Yes, of course. It's kind of obvious, right? So we are done. Interestingly, some special random processes can be described, fully characterized by two lines. It's a Bernoulli with parameter p. And that has two lines. Xn's random variables are Bernoulli random variables with power p, and these countably infinite random variables are independent. Got it? Now, here goes the question. What is the mean function or mean path over the ensemble average? As we've already discussed, this is a constant function. Be careful. P for all n. So it's a function of n. It's not a scalar p. It's a function, constant function that is p for all n. So it's very, very different from the sample patterns. This question, you do it yourself. I will move to the next example, discrete time continuous random process. This is called, in communications engineering, a white Gaussian, a discrete time white Gaussian noise process. And it's defined like this. Similar to the previous one, each x of n as a random variable is zero mean Gaussian with variance sigma square. And again, we have countably infinite number of random variables. They are independent. And of course, identically distributed. And you can easily show that using the same method, but now using the nth order joint PDF. For example, you can find any nth order joint PDF, and you can show easily using the IIDNIS, they are all consistent. So these two lines, xn's are zero mean, variance sigma square Gaussian, and xn's are IID, you are done. And what about the sample path? It's a zero function. The sample path is zero for all t. Got it? Again, this is very, 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 very different from any sample path. Got it? So here I emphasize in the handout that two things you need to remember. In general, it's extremely, extremely difficult to fully characterize a random process. And second one, as I just said, that the sample path may be drastically different from mean path. In this case, it seems that full description is hopeless in general, and it's one of the representative paths, maybe far from sample paths. We are doomed? No, there are, as I told you in the beginning, there is a very small, very special classes of random processes called stationary random processes. Even though this subset is very small, in many engineering problems, engineering science, financial, signal processing, it's very useful to model a random process, a stationary random process. And that's what we are going to see here. The first, second, third, nth order stationarity, or stationarity to the first order, stationarity to order 1, stationarity to order 2, stationarity to order n, are actually, these definitions are all related to the Kolmogorov's extension theorem. Because in order to fully characterize a random process, what did Kolmogorov say? You have to find the first order PDF or CDF or PMF of a random process, second order, third order, and so on. This definition is related to that. So here goes the stationarity to order 1. What does that mean? So in order to fully characterize, you may want to start from the first order PDF of a random process. And in general, what is that? That is a PDF parameterized by time t. And here it says that it does not change. So as you see, the CDF of x of t, here you may fix t as t0, then you have a random variable, right? And this does not change. So f sub capital X of t0 over x equals capital F sub x of t1 of x for all x. Here, be careful. Left-hand side is written as a function of x, and also right-hand side is written as a function of x. So they are both function of x's, and they are equal for all x. Okay? So it does not change, of course, for all t0 and t1. Let me use capital T. Okay, this is the this could be a discrete set or a continuous set. It could be a finite interval, but as far as you have uncountably or countably infinite number of time instants, then it's a random process. Got it? But be careful. How can you rewrite this one? That is this idea. Okay, see that? Do you see the difference? Here, I have chosen 2 time instants to describe stationarity to order 1. That is somewhat strange, right? But here, you choose 1 time instant, but you take an offset, capital delta, and say that your CDF at time t and your CDF at time t plus any offset delta, they are the same, got it? And you may say that it's the same, right? Let me say t equals t1 and t plus delta equals t2. Then they are the same. You are right. However, in order to extend this definition to stationarity to order 2, 3, n, you need this one. Got it? Now, before we move to the stationarity to order 2, let's see the interesting commonalities of stationary random processes to order 1. So this is again the set of all random processes. And here goes, I exaggerate a lot, okay? Stationary to order 1, okay? Even though the subset is invisibly small, I exaggerated. Now you choose any member of this subset. Then you may say that, okay, they share some commonality. What is that? Of course, by definition, each one's first order CDF does not change, even though time evolves. But as we've already defined, what about the sample path, the mean path? So we compute the expected value of x of t. Now, for each t, you have a PDF, CDF, or PMF, but that does not change even though you change t. What does that mean? Your sample path, mean path is constant for all t. Okay, so this is constant for all t. Okay, whether it is a discrete random process or continuous random process, continuous time random process or discrete time random process. Okay, if it is stationary to order 1, its mean path is constant function. It's a simple consequence of the definition. Got it? It is not necessarily 0 for all t. It could be p for all t. Okay. Now, what about the expected value of x squared of t? By the way, what is the meaning of x squared of t? In electrical engineering, we call it what? The expected value of instantaneous power, right? So if you have signal x of t, x squared of t is called instantaneous power. So power at specific time t. So given a random process, if you square it, you have a new random process, right? So it's like here is the underlying probability space, and you have a random process that is a mapping rule. But before you observe, you have a squaring device that takes a time function and generates another time function. And this output is called x squared of t in this case. Got it? Now, what about the ensemble average of this instantaneous power random process? It's very simple. Again, you handle this one as a random variable by fixing t to t0. Then what do you have? What do you need? You just still need the first order PDF. So x squared density of x of t of x dx. Nothing difficult, okay? You are reusing the results from your random variable study. And this expected value of x squared of t is called the ensemble average power of x of t. Got it? When we had a deterministic signal, average power was defined as what? Actually, it was defined a strange way like this. Okay? This is called the average power. So be careful. Okay? Given a time function, average power is what? Energy on a finite interval divided by the length of the interval when you take the interval size to infinity. Got it? If it is periodic, you don't need the infinite interval. You just need one period or any finite number of periods. So here goes the result. So what about this one? The ensemble average power of first order or stationary random process to order 1 is what? Again, this PDF does not change. What does that mean? It's a constant function of t, which means it's constant. So you may say that, okay, let me say some constant for t. So if you define a random process that is stationary to order 1, what is the consequence? Its mean path is a constant function. Its average power is a constant function. What about third order? X cubed of t. Still constant, right? Now, let's move on to the stationary to order 2. And so you want to define stationarity to order 2. What would that mean? In the first order, or stationary to order 1, you'd have chosen some t. And for any offset delta, this PDF does not change. Now, to the stationary to order 2, you're also motivated by the Kolmogorov's theorem. So you feel that, hey, I have to handle second order CDF or PDF or PMF. Now, this is a two-dimensional function. And what would be the stationarity? Here goes the power of that capital delta. You put the same offset to T1 and T2. And this function of x1 and x2 is the same function, same two-dimensional function for all delta. Okay? So your second order joint CDF of random process does not change under time shift or time translation or your choice of the time origin. Got it? But be careful. If you choose different time interval between T1 and T2, the joint CDF, second order CDF may change. So let me draw a two-dimensional plane. And this T1 and T2 is what? The two sampling instants. Now, each point on this two-dimensional plane gives you the pair of time instants, right? And what does this stationary to order 2 mean? From this point, your arbitrary choice, you draw a line with slope 1. Then, what are the commonalities of the points on this line with slope 1? What are the commonalities? The first coordinate minus second coordinate does not change. Just think about this one. Suppose this is 3.2, then what would be this one? 2.3. This would be 0.1, right? What's the difference between T1 and T2? -1, -1. All the points has difference T1 minus T2, -1, right? What about you choose different point here? Now you take if you draw a line with slope 1, all the points on this line have commonality that time difference, actually subtraction relative to T2 if you want, T1 minus T2 is the same. And now, in general, on this line, the second order PDF may differ. However, under the assumption of stationarity to order 2, what happens? All the time pair gives you the same second order PDF. On this line, all the different points have the same second order PDF. Be careful here. The second order PDF for this line may differ from second order PDF for that line. They may differ, but on each line, the second order PDFs are the same. Got it? This is what? This is stationarity to order 2. Got it? I'm not saying that any second order CDF is the same. I'm saying that as far as two points, time difference is the same, the second order PDF is the same. Now, let me ask you a question. What about the relation between stationarity to order 1 and stationarity to order 2? Anybody? If a random process is stationary to order 2, it's stationary to order 1, always. Why? Why? Why do you have that? So we need to find the first order CDF. Now, from this second order CDF, how can you find the first order CDF? Simple. You just plug in infinity to, for example, here, x2. Then what happens? The left-hand side becomes x of t1 of x1. What about the right-hand side? Capital X f sub x of t1 plus delta of x1 for all x1 for all delta. What does this mean? It's stationary to order 1. Got it? So stationary random process to order 2 is automatically stationary to order 1. So let me go up and draw a subset of subset. Stationary to order 2. Got it? What about stationary to order 3? How do you define it? As the Kolmogorov's theorem says, you have to talk about the third order joint CDF, PDF, or PMF. Then what? That joint CDF does not change under any time translation, any choice of time origin, 0. And that can be formally written as what? Something like this. So let me just jump to nth order stationarity, stationary to order n. So 1, 2, and many, right? And this starts from nth order joint CDF of the random process. So the left-hand side is simply the nth order joint CDF, where you have chosen T1 through Tn from any point in the n-dimensional space R to the n. Each point represents the nth of sampling instance, and you have the nth order CDF. Now, you want to claim that that does not change under origin translation. So you add capital delta to T1, to T2, to any Ti. So here goes another joint CDF, and so the joint CDF. The difference is that time instants are offset by delta. These two functions of n parameters are the same for all capital delta. That is the definition of nth order stationarity. Now, question. What about its stationarity to n-1, n-2? Second, 1. What do you think? As we've done already, if random process is stationary to order n, then it's stationary to order n-1, n-2, dot, 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 stationary to order 2, and stationary to order 1. Got it? So for any finite any stationarity to order any finite number, we can easily define. And now we have 1, 2, and many, but what about infinity? And you may say that, oh, what do you mean by infinity? What I'm saying that for any natural number n, it is likely that there is a very special group of random processes that is stationary to any finite order, millions, trillions. And what would be the definition of such a random processes? They are strictly stationary, which means that they are stationary to any finite order. Got it? So eventually we have here very small set, strict sense stationarity. And they are all motivated by the Kolmogov's extension theorem, or consistence theorem, or existence theorem. Got it? And they are all common in talking about some finite order joint CDF, PDF, or PMF over random process, or a characteristic function if you want. And for any nth of the sampling instance, if you shift the origin, time origin, by moving your choice of the time origin, they does not change. They do not change. In the case, it's station. Got it? So we've defined strict sense stationarity and stationary to any order. Now, let's go back to our second order stationarity again. And now here goes something very useful and interesting, and which is also a topic of the part of the section 6.2, I believe, but it is the more in-depth discussion on this topic will be deferred. But anyway, let's see. So here goes some strange thing. And it seems you've seen this or something similar. Capital R sub XX of T1 comma T2. And it reminds you of what? The correlation between two random variables. So what was this one? Capital R sub capital XY. with or without comma, but people love without comma, and it's defined as the expected value of the product between two joint random variables, x and y, right? So recall this definition, and now take a look at this notation and its definition. So take a look at the right-hand side. You have expected value of random processes sampled at different time instants, or T1 could be T2, but anyway. At each T1, what is x of t? It's a random variable. At T2, what is x of t? That is another random variable. So precisely speaking, this right-hand side had better to be written as capital R sub capital X of T1, capital X of T2. But as I told you long ago, typewriters did not have subscript. So they avoided this kind of notation. Of course, now any word processor can handle this notation, but still the tradition goes. So they love to write this way. But anyway, this is what? This is a two-parameter function. And what are the parameters? T1 and T2. So this is a two-dimensional function. Got it? So this notation makes sense, right? Because when we define a function, we name a function. So we name function as f. And then we put colon, and we put the domain, and right arrow, and codomain, right? Similarly, you may just say that this is a two-dimensional function, capital R sub xx, colon, R square into R, something like that. And what is this name of this function, this two-dimensional function? It's called the autocorrelation function. Here, auto comes because you have a single random process x. So from one random process, you have two random variables. In that sense, it's called auto. What if you have two random processes sampled at different time, x of T1 and y of T2? In that case, their correlation is called cross-correlation function. Anyway, so here goes the definition. And of course, the question is, what would be the property of this correlation function when your process x is stationary to order 2? What would be that? And let's just simply use our definition. So x of T1, x of T2 equals what? Any expectation of anything equals what? Integral or summation of value times probability. So you have value, let's say x1 and x2, probability, let me use the joint density of x of T1 and x of T2 as a function of x1 and x2. And then let me integrate over x1 and x2. So this is the definition if joint density exists. If you don't like that, then use the Stieltjes integral and joint CDF. But anyway, so our focus is here because we assume the process is stationary to order 2. How do you want to change? Of course, you put capital deltas here and there. So you have plus delta and plus delta. And what is this? This is a function of T1 and T2 and parameterized by delta. But due to the stationarity, this delta doesn't matter. And now we again use this two-dimensional plot. And again, I draw a line with slope 1. And on this line, what kind of commonality do we have? Due to the stationarity, this correlation does not change, right? What about on this line? The correlation does not change. But these two correlation values may be different. Got it? And here goes something very confusing but very useful. What if we define tau as T1 minus T2? So what is tau on this line? -1. What is tau on this line? Negative some 6, something like that, right? Now, this T1 minus T2 can be used as a new parameter that distinguishes two correlation values. So we introduce this time difference and use it here like this. So you fix T2 and you replace T1 with what? T2 plus tau. Or you may just write, let me use T plus tau and T. Got it? So it's a kind of change of variable. Instead of having T1 and T2, you have T and tau. Got it? And this tau corresponds to the offset, right? Now, what if you have stationary random process to order 2? This correlation function is what? A function only of tau. Got it? As you've seen already. Now, here goes the most important confusion. See that? Here, what is this R sub xx as a function? It's a function having R squared as the domain. Now, what about this one? This is a single parameter function. So its domain is R. Can these two functions be the same? In general, you never say two functions defined on the different domain are the same. They are different functions. However, their function values are the same for the same tau. So this is an abuse of notation. Okay, this function is a two-parameter function. This function is a single parameter function, but they have the same name. Okay? And that is one of the most confusing convention among the people handling random process. So this is an abuse of notation. But you don't want to introduce a new name for the function of tau. So this single parameter function parameterized by tau, that is T1 minus T2, is very useful when you are given a stationary random process to order 2. And this single parameter function is called what? Usually the autocorrelation function of a stationary process to order 2. Got it? However, there is another definition. Hey, what if just the moments are stationary? What does that mean? The sample path gives you the mean path. This autocorrelation function may give you autocorrelation function parameterized by tau. And what if expected value of x of t equals constant for all t, and the autocorrelation function is a function of tau only, time difference only. So since it's difficult to check whether a random process is stationary to order 2, but sometimes it's easier to check its mean path, and the autocorrelation function is a constant and a function of tau only. We define something new. A random process is x of t is wide sense stationary. What does that mean by wide? In Korean, 광의의, 넓은 의미의. So in a wide sense, it's stationary. But strict sense, it's not stationary to order 2. So Here goes a simple lemma. If x of t is stationary to order 2, then it's y-sense stationary. Vice versa? No. Y-sense stationarity only talks about the expected value of these two things. The converse is not necessarily true. And here goes another one. You can define, so have I, yeah, y-sense stationarity. Yeah, here, y-sense stationarity. We may define covariance function like this, or autocovariance function. Now you subtract the mean value and then compute the correlation. And as we've done for two random variables, x and y, we can define the autocovariance function of a random process. Again, it's a two-parameter function. However, what happens if the process is stationary to order 2? Same, right? We have covariance function, which is a function only of tau. So we introduce c sub xx of tau. Right? And the relation between the autocorrelation and mean path, mean value, is this one, as we've seen already, because covariance of x equals what? Correlation of x minus mu x squared. Same thing. Okay? Now, there could be a random process that does not have constant mean path, but its covariance function may be a function only of tau. For that, we define what? The covariance stationary random process. So covariance stationarity means what? Covariance stationarity means this one. Its mean path is not required to be a constant. However, after you subtract that non-zero mean path, you have y-sense stationarity after you subtract. Got it? And that is very useful because, for example, you want to handle cos p 200. And as you can obviously see that its mean path moves. Sometimes it's a bull market and it's a bear market, something like that. And it's never second order or first order stationary because you have an obvious mean that is not constant. So one of the simplest way, I'm not recommending this, but simplest way is to subtract that long-term average. And then you plot. Then it may well modeled as a y-sense stationary zero mean random process. And then you do something. Right? So this covariance stationarity is very important and could be useful in some mathematical modeling. Now, since we do not have much time, let me quickly just mention example. You've seen this deterministic random process already. Here, A omega theta before could be random, but here we restrict that only theta is random. Got it? So A and omega, amplitude and frequency is fixed here, and theta is uniform continuous random variable on 0 to 2 pi. Now the question goes like this. Is this y-sense stationary? In order to prove that, you need to use the definition. So you first find the mean path. What about that? Each sample path is a cosine function, right? With the same amplitude and same frequency. However, their offset, phase offset, could be different from 0 to 2 pi. And interestingly, from this 0 to 2 pi-ness, you have exact opposite sample paths. And each of them, when you compute the mean path, they cancel away. And you have what? Zero function. This is the mean path is 0 for all t. So first hurdle is overcome. What about the autocorrelation function? That requires you to use the trigonometric identity, but just take a look at that. It's a high school math. So by definition, you have a cosine omega t plus tau plus theta times a cosine omega 0 t plus theta. Now, what is random? Only theta is random. And you average over theta, which means that integration from 0 to 2 pi, 1 over 2 pi times d theta, times, of course, the integrand. Then you have this nice function only of tau. So it's a function only of tau. So it's Ysen stationary random process. Is it interesting? Each sample path is a cosine function, but random process is Ysen stationary. So you feel that this Ysen stationarity is not a good definition in some sense, right? And you are right. Some wide sense thing has limitation. However, it's better to have nothing. Okay, so you must be careful. Okay, we've already covered this stationary to order n and straight sense stationarity. And unfortunately, we couldn't reach this statistical independence. But I can finish. So what about you have two random processes and want to say that they are independent random processes? And we can go back to our independence of two random vectors, finite length. How did we define? Any event in terms of random vector x and any event in terms of random vector y, if these two events are independent events, then the random vectors are independent. That is, of course, the definition. However, whenever you have two random vectors, you have joint CDF of the random vectors. And what happens? Independence means that joint CDF factors into marginal CDFs. Now, we have two random processes, and you want to establish they are independent. How can you do that? We combine our previous experience for the two random vectors and the Kolmogorov's theorem. Here again goes the greatness of the Kolmogorov's idea. So what we do is that we just sample, we take any finite number of random variables from X process, and we take any finite number of random variables, take samples from Y process, and their joint CDF's factors. Then they are independent. What about three random processes independent? Again, you combine your experience of handling three random vectors and Kolmogorov's extension theorem. So statistical independence, when I was taught about this notion, I got a lot of confusion. However, if you just combine this idea of independence of random vectors with Kolmogorov's theorem, it's just obvious. The definition is just natural. Got it? Similarly, if you do not want this strict sense independence, you may talk about some Y-sense stationarity, but it seems time's up. So let me just stop here. Okay, unfortunately, I couldn't finish. Okay, that's all for today.